the status on the SNV-12 before we start is that if you want an SNV-12 IP right now with SVM-3 modules, you can get it right now. But if you want it to work with SVM-3s and SVM-2s, that's going to be 30 days. And so that's our status. And at this point, I'm going to pass it to Carol. So Carol, you want to say a few words?
Thank you, Dave. We appreciate your time in attending the first monthly JPS Dealer Representative webinar. As Dave said, we know your time is important. The next monthly webinar will be Monday, May 21st. All dealer and representative monthly webinars will begin the same time of day as today's webinar did. We will send you the schedule for this year's monthly webinar series later this week. The dealer and representative webinar series is a continuation of the sales and marketing support for you, our valued sales partners. We encourage you to review the material on the JPS website. We continue to add sales and marketing support material, including product videos, which is increasing all the time. Thank you again for taking the time from your busy schedule to join us for this important product webinar. At this time, allow me to turn it over to Iggy. Thank you, Iggy.
Welcome to our first webinar, and in this session, we're going to talk about analog receiver voting, and particularly our SNV-12 analog receiver voting product. So the next a few slides, I actually am reusing slides that I used a few months ago on an APCO regional chapter conference. It was kind of a learning experience for some of the members, and we talked about analog voting. It was very agnostic. Didn't want to talk about SNV-12s in particular. So to a lot of you, a lot of these slides might be fairly basic, but towards the end, we're going to talk about the SNV-12, particularly analog voting, analog backhaul, as well as our new digital backhaul application, which you can find pretty exciting. So let's go ahead and get started. I wanted to really talk about some of the basics of radio coverage, and this is a perfect primer to discuss how we use repeaters and how we use analog voting to select these repeater sites, particularly when I have multiple repeaters. So I'm going to start very basic, and I'm going to talk about simplex communications. And I think the Latin term for plex is a weave or a path. And in simplex communications, we use a single path to support the receive and transmit component of our communication. So in terms of simplex communications, the receive and transmit audio are the same frequencies. This type of communications is still widely used today, car-to-car, man-to-man, simplex communications. But the problem with simplex communications, however, is some of the physical constraints of the radio systems, and that can also include transmit power, sensitivity of the receiver, antenna, physical obstacles such as building or terrain. But to alleviate this coverage issue, with regards to these two different radios working in this simplex environment, we can often include a relay site or a repeater site. And this repeater site now becomes what we call a duplex system. If we look at the Latin term for plex, meaning path, and duo, we now have two paths, separate paths for the receive communications and a separate path to transmit. So in this type of architecture, I can transmit at one frequency, and my repeater or my relay site can receive at that frequency and then rebroadcast at a completely different transmit frequency, where my subscriber units can receive at that very same transmit frequency for my relay site. So this helps alleviate coverage issues, and it's a great way of expanding my coverage region. So handheld radios also can benefit from these repeater sites, but the handheld radios also have a different type of constraint. It's very similar to the mobile radios, and this could be defined as really the sensitivity of the receivers in my handheld radios and the fact that I have a unity gain antenna. So even if I have a relay site or a repeater site, constraints of that handheld radio suffer. Again, to alleviate this, we can also add satellite receiver sites or distributed receiver sites to increase the coverage area. And then we can backhaul that audio through various transport methods, which we'll talk about shortly. So if I design my radio system properly, I create coverage with my satellite receiver sites. I can roam throughout my area of operation, and hopefully I can hit one of my receiver sites and backhaul my audio to either a dispatch center, call center, or to a system-wide transmitter and rebroadcast my communications out to the field. So receiver sites are very important in creating coverage, but we also run into an issue when we talk about what do we do with this audio. And typically we would use a comparator or a voter, and in this case, since we're JPS, we're going to talk about our SNV-12 analog receiver voter. And the purpose of that voter is to simply select a single receiver site of the highest audio quality and reuse that audio again to rebroadcast or deliver to the call center or the dispatcher. How do we measure or determine the quality of these or satellite receiver sites? And we have a couple methods, and those of you that have experience with the SNV-12 may have noticed that we do have a method of voting either FM receivers or analog receivers. So some of you may be confused of why do we have two? Why can't we just have one? So I'm kind of explaining interesting attributes of FM receivers or phase modulated receivers compared to AM or amplitude modulated radios are a little bit different. So in this diagram, I've got a little plot here that signifies the distance between my transmitter and my satellite receiver site, my terrestrial site. And so what I wanted to really depict here was how does the audio sound as I move my transmitter or my subscriber unit that might be in my hand or in my vehicle. As I move away from my receiver site, what does this quality of the audio sound like? The correlated audio, the human speech that we're interested in. Also, how does the noise affect the receiver site? I've got the little plot down here on the bottom, which depicts the audio at the receiver site with respect to the noise, as well as the noise with respect to the distance or the margin between the transmitter, the subscriber unit, and the receiver site.
323 to 584. 25. Adam Young, 1955. Okay. 3 word pentagram we refer to. I believe it was called on channel 1. Okay, we have 482 coming out there for the end.
One interesting thing you might notice is that the audio level stays the same, and that's due to the attribute of the detector or the discriminator at the receiver site. So we're really trying to detect phase or variations in frequency, and the detector detects that, converts that into a fluctuating DC signal, which we excite a speaker, or in this case, we excite the voter. And so we consume that audio, which is then voted upon. But as we create margin between my transmitter and receiver site, not only does my audio stay constant, but my noise increases. And the reason that noise increases as I create margin between my transmitter and receiver is because of the FM limiter at the receiver site. The FM limiter lacks the bandwidth or dynamic range to actually remove the noise, which is really amplitude. All right, so we're trying to measure frequency, which the discriminator does just fine. That's why the audio stays the same until I hit my capture effect and I lose the audio completely. The important thing about FM receivers is that the noise varies as I create margin between my transmitter in my car or in my hand and my satellite receiver site. So it's kind of keep that in the back of your mind. And so when we vote with the SNV-12, we're continuously analyzing the spectral noise above 2.2 kilohertz. And we use digital filters in our digital signal processors to analyze that audio. And we analyze all the satellite receiver sites for the lowest amount of audio energy above 2.2 kilohertz. We vote that singular receiver site, and we pass it on to the dispatcher or a system-wide receiver. So FM communications, we measure noise only. In terms of AM communications, particularly aircraft radio systems, and one interesting thing about voters is AM voting is predominantly used throughout the world to vote air traffic control. Air traffic control primarily uses VHF AM communications. We do have a number of SNV-12 systems deployed throughout the world that are voting air traffic control. Voting AM is a little bit different than FM. So I've got the same layout here. I've got a bunch of my terrestrial satellite receiver sites, and I'm flying around in my aircraft, and hopefully I am within coverage of one of my receiver sites. And as I create margin between my aircraft, which is a transmitter, and my terrestrial receiver site, we see some interesting things with regards to the correlated audio, the audio we hear from the pilot, and also the noise of the system.
Solution 542, turn 10 degrees left, please.
10 left, Solution 542.
Solution 542, turn right, heading 340.
340 heading Solution 542.
Eagle 3655, turn right, heading 250, descend and maintain 2000.
Heading 250, descend to 2000, 3655. Tower 120.
So if I look at the plot with respect to distance between, or margin between my transmitter and my receiver, you'll notice that the noise stays constant. Unlike in FM communications, the noise increases as I create margin between my transmitter and receiver. In AM communications, in particularly this form of air traffic control, the audio starts diminishing due to the inverse square law and the distance from between my transmitter and receiver. The audio is such low amplitude that the detector at the receiver site is no longer able to discriminate or react to the amplitude changes. So what happens in AM communication is the noise stays the same, because that noise is inherent or native to the thermal noise of the receiver at the receiver site. So that's not going to ever change. The only thing that changes in AM communications is that the audio, the correlated audio, the speech that we're interested in, begins diminishing. So in the SNV-12, the JPS analog voter, in AM mode, we vote signal to noise, which is the difference between the correlated audio and the noise floor, which is the inherent noise inside the receiver. So the larger the difference between correlated audio and the noise floor of the receiver, we're going to vote that audio because we know that of high quality audio. So as the aircraft moves into a different region of coverage of a receiver, the inverse is going to happen. The audio will start increasing, becoming better, create a larger difference in signal to noise ratio with respect to the noise floor, and then we vote that site, that singular site only. All right, so it's a little bit difference between AM and FM voting. And the reason we do that is because if I vote FM, which is predominantly obviously used in commercial and public safety, we will measure only audio content above 2.2 kilohertz. We use digital filters. For us, it's easy to do that. In AM communications, since the noise rarely changes, we need to measure the correlated audio, which is human speech, between 300 to 800 hertz. We also use discrete digital filters to do that. In AM communications, we have to separately measure the noise as well as correlated audio, which is a little bit more difficult to do, but we can do that. In FM communications, we don't really care about the correlated audio because that never changes until we hit the capture effect. Right? So hopefully that kind of clears up the difference of how come we don't measure signal to noise in FM, because we don't really need to. We're just going to measure the spectral noise above 2.2 kilohertz. As far as receiving is concerned, as long as I have my receiver sites set up throughout my region, I can roam with my subscriber unit between these receiver sites and seamlessly hand off my communications, and it should be completely transparent. So we set up what we call the voting criteria, and that's set up in the control processor module, which is the brains of the system. And by default, I think our criteria is the noise floor has to improve by 1 dB for a period of 250 milliseconds before I move to that other site, so we don't create chattering between sites. And if I align my receive audio delay perfectly, you should not hear the handing off of the receiver sites as I move throughout my region. So that's the essence of perfect voting. And so some of the talk out techniques we use, and one of the most common is to use a single wide transmitter site. I have one set up here. I vote one of my receiver sites. I deliver the audio to one of my SVM-2 modules on the right side of the chassis. I have 12 sites I can vote, and then I determine the spectral noise above 2.2 kilohertz, and I repeat that audio out a singular high power region-wide transmitter. I can also deliver the voted audio to the dispatch center or a dispatch console, or I can mix. I can do both. I can repeat as well as deliver audio to the dispatch center, and I can create priorities. So if I want my dispatcher to have transmit priority, they can essentially override any repeat transmission. So there's a lot of flexibility in the SNV-12 to meet anybody's need. But so this is probably the most common configuration that we see out in the field. And in fact, if you talk to Benny Hillman, he's our SNV-12 guru in the factory there at JPS. I often call him about voter issues. But when I talk to customers, and I know Benny does the same thing, is if we have a lot of problems, if the customer has a lot of problems with their voter, we often tell them default all the switch settings or the configurations of the chassis, which means that's the state that the chassis has been delivered from JPS, and it will probably support a single region-wide transmitter. All right, you have to set up the audio levels, set up the status tone, the pilot tone, but the default configuration of the voter will support this single region-wide transmitter right out of the box. So setting the chassis back to default is a great way of troubleshooting and essentially starting from scratch. So the other configuration that's often deployed with analog voters, particularly the SNV-12, is multicast. And multicast is interesting because now each of the receiver sites, the satellite receiver sites, also has a capability of transmitting. And each receive frequency at each of the receive sites are different, as well as the transmit frequencies of each site are different. So this requires a subscriber unit, whether it's a mobile or a portable, as they move into different regions, they're required to switch their channels. A lot of commercial systems are deployed using multicast. Again, requires the user to change the channel on their subscriber unit. A little bit inconvenient, but it's a very economical way of creating more coverage. When my receiver site in a multicast environment receives, we will naturally vote that site, deliver the audio to the voter, and through multicast, we can deliver to multiple transmitters throughout my entire region, and then I can start communicating with others that are completely outside of my region. But by multicasting and broadcasting throughout my region, I can then create two-way communications with others that are outside of my region. The only inconvenience, again, is that the users of the subscriber units must change their channels. The other talk-out configuration is what we call simulcast, very similar to multicast, except my transmit and receive sites at each of my remote sites, the receive frequencies are the same, identical throughout this region, and my transmit frequencies are also identical. So the beauty of this is that my subscriber unit, I do not have to change my channels as I roam throughout my region. I stay at my single channel. The problem occurs with regards to interference due to the relationship of different transmitters out in my region, particularly in the overlapping regions, which we sometimes call the non-capture region. And if we talk about the capture ratio of an FM radio, well, if I am in overlap region, well, I'm within the capture ratio of 2 transmitters or 3 transmitters. And in essence, I will be receiving communications from these remote sites into my subscriber unit. I'll have destructive interference. I'll have some buzzing. The audio will be significantly degraded. So it's not an ideal situation, particularly in that non-capture region, the overlap region. So we can support simulcast communications. Again, all the receive frequencies are the same at the satellite sites. The transmit frequencies are all the same, but we have to synchronize the audio. And we do that with third-party devices. Sometimes we call those distribution amplifiers. And distribution amplifiers allows a technician or engineer to align the transmit audio such that the audio in the non-capture region is completely in phase, and they do not cancel each other out. We don't get the inherent humming between the adjacent transmitter sites. So we don't do this. There are third parties that provide distribution amplifier solutions. Ed O'Connor's, as we all know, Simulcast Solutions is a great person to talk to when dealing with simulcast. So a lot of engineering involved, requires lots of timing, GPS, rubidium, time sources. The audio has to be perfectly aligned. Some of the other talk-out configurations is manual steering. by using function tone steering, RS-232, or contact closure from the dispatch console. We can deliver transmit audio to what we call receive groups, and we can support up to 14 different receive groups, which is really a consolidation of different receiver sites and supporting transmitter sites. So at the dispatch console, I can steer to a specific receive group and begin communications with the subscriber units in the field. If a receiver in the field happens to vote, we can also deliver that audio back to the transmitter or the dispatch operator. But that dispatch operator has to have the wherewithal to physically or manually steer to that transmitter. So there's a little bit of work involved as far as the dispatcher is concerned, but manual steering is still very common. We vote receiver groups, consolidation of receivers with one or two, maybe multiple transmitters within that receiver group. So each receive group is really an environment in itself. But this, again, requires the dispatcher to have the wherewithal to know what site or receive group is receiving and have the ability to manually steer to that site. The SNV-12 analog receiver voter also has an automatic steering function. We also still vote receive groups, but what STARS performs, which stands for Smart Transmit and Receive Steering, is that when I have a receiver voted in a receive group, the voter will automatically select the transmitter within that region, and the dispatch operator, they no longer have the responsibility of manually steering to that transmitter site. It can be overridden at any time, as well as allows that dispatcher to not have to worry about the transmitter and having to steer manually to that transmitter. So let's talk about receiver links real briefly, and this is kind of leading up to IP backhaul. And some of the most common backhaul methods you see here are lease lines, voice grade. They could be conditioned lines. They could be 4-wire, 2-wire, telco lines. T1 microwave is also very common, as well as continuous UHF RF links. By far, lease lines are the predominant backhaul method in analog fashion back to the voter, have been effective for many decades. All right, so let's talk about voting receiver IP backhaul, because nowadays, as we all know, IP networks are very prevalent, very easy to deploy, and ROIP is very reliable technology. And we've had ROIP products since the late 90s, and most of our products at JPS have some form of ROIP capability. There's a lot of problems involved in this, and if you've seen our manuals for many years, have always advocated not using ROIP in voting because of a couple constraints. And so one of the problems with voting over ROIP or IP networks is network latency. It's not really the network latency is a problem. I'll show you a little bit later why that's not a problem. But what's a problem in voting IP networks is the unpredictable nature of that latency, and jitter throughout the day or throughout the week can play havoc in voting systems. And we'll talk about how we vote, the process of voting in a synchronized fashion. The other disadvantage of voting over these IP links using ROIP is loss of fidelity due to the so-called lossless conversion of the vocoders. We have to convert the analog audio from the receiver side into a digital form, and we have to compress that audio such that it'll effectively or economically be placed into the payload of a packet and delivered over the network. We deconvolute that audio through a decoder, and we lose the fidelity of the audio. Some of the fidelity we lose is a spectral noise, which is important to proper voting. A lot of disadvantages and advantages of IP networks. Let's take a look at the voting process, and we're going to talk about analog links. Again, lease lines, T1 microwave, continuous RF links, again, analog links. Got my voter here on the left with 3 site voter modules, and these site voter modules support the receiver sites out in the field. And I've got my subscriber unit. It's about to fully quiet a multiple of these receivers, 1, 2, or all of them at the same time. And again, I have my analog lease line links. When I fully quiet or unsquelch a receiver site, I deliver the audio to the voter, and the voter is going to be aware that the receive sites have unsquelched, and we begin the voting process. And the voting process involves measuring and analyzing the spectral noise above 2.2 kilohertz. All right, so the process is a round robin. We go through each of the site voter modules, analyzing the spectral noise, and then we select a site, and we vote that site. We deliver to the transmitter or the dispatcher or both. As you may have noticed, my data is being delivered sort of offset here, and this could be due to a lot of things. It could be physical distance in this lease line. There could be other equipment that has sort of process delay. For the most part, this audio from this receiver site is being delivered late. And through the round robin process of the voter, we're measuring spectral noise. The voter is going to look at this link that's being delivered late, and it's going to say, hey, this site's very quiet. I'm going to vote that site, which in fact is not the site that's being fully quieted. I'm actually voting a noisy site, and I'm effectively misvoting. The good thing about analog voting and the process delays in analog links is that this delay or this latency is repeatable or it's continuous. So throughout the day, throughout the weeks and months, this delay is repeatable. All right, so that's good because in our site voter modules, I can apply what we call receive audio delay. If for all intents and purposes, I'm essentially moving the quickly arriving audio back a few milliseconds, and we can effectively measure the spectral noise in a simultaneous fashion, thus preventing misvoting. All right, so receive audio delay is important. I can apply delay to the early arriving audio, store it a few milliseconds, wait for the late arriving audio to arrive, then we vote simultaneously. And again, in analog links, audio delay is a perfect solution for misvoting because in analog links, that latency is repeatable, it's continuous. All right, so let's look at a network link scenario. So I bought a couple NXUs, for instance, or I don't know, any ROIP device for that matter. But the important thing is I'm taking the analog audio from my receiver site, delivering it to an ROIP device where I compress it. I place those packets as the payload in a TCP/IP packet, deliver it across my IP network. At the head end, which is my voter, I can deconvolute that audio, convert it back into analog information, and deliver it to the voter. And I'll be a hero because I'm saving a lot of money decommissioning my lease lines. All right, so same scenario occurs. I'm going to fully quiet my receiver sites. I deliver audio, I compress over the network, I decompress, and I deliver the audio to the voter, and I vote precisely at the same time. I do a round robin, continuously measuring spectral noise. All right, so that's what the voter does, looking for the least amount of noise from one of these receiver sites. And let's say, for instance, I deploy my ROIP network, I don't know, in a maintenance period, 2 o'clock in the morning. If there's not a lot of radio traffic, I can deploy my ROIP links. And lo and behold, I notice that one of my receiver sites is slow. And this is due to the latency of my TCP/IP network. No big deal. I can go into my SVM-2 modules. I can adjust my receive audio delay such that all the audio is arriving at the same time. I'm good to go. My system's voting properly. The problem occurs throughout the day is that the jitter changes. So 10 o'clock in the morning, noontime, I get a call as a technician or an engineer, hey, your system's not voting properly. Well, I go out to the site, and due to the saturation of the digital network, passing video, people sending data over to the networks start to saturate and slow down and speed up. And my audio delays are now skewed, and I'm misvoting. Right? So I go in at noontime, I realign my receive audio delay on my voters. Everything's voting properly. I get another call at 9 o'clock in the evening saying my voting system's not properly voting because the networks have desaturated and my latency latencycy is changed, and it changes throughout the day, and you start chasing your tail. So you're going to have a technician manning that voter on a 24-hour basis, changing the receive audio delays, and that's not acceptable. So that's why we've never advocated voting over network links using devices such as the NXU2A. I mean, it's a great device for eliminating lease line, but the problem is the unpredictable nature of the jitter, or the latency associated with TCP/IP networks. And as I mentioned, in analog links, they rarely change, but in network links, they are changing constantly throughout the day. So that's a big issue. The other problem we see with voting over IP is the so-called lossless vocoders that we use. We predominantly use a MuLaw or a G711 vocoder just to maintain as much fidelity as possible. So as we deliver the analog audio to the first ROIP device, which we begin the compression process to deliver as a payload over a network packet, well, that's good, well and fine. But when we deconvolute at the far end with another NXU2A device, we lose the spectral content of that audio due to the the conversion loss of the vocoders. And a lot of people claim, well, these are lossless vocoders. There's no such thing as a lossless vocoder. There's always a price to pay in terms of fidelity. We're saving bandwidth. We do lose some of the spectral content. So what's important to the voter? The voter, we want to analyze 2.2 kilohertz and above the spectral FM noise of the receiver site. And because of the lossy nature of ROIP conversion, we're unable to properly or accurately measure that spectral noise, which is very important to proper voting. So we got two things against us: the latency, the jitter, as well as the lossy nature of the compression algorithm. All right, so let's talk about receiver IP backhaul, particularly with the SNV-12. As you probably already know, we do have a solution that allows us to vote over IP links. And this is a kind of a little close-up of our analog SVM site voter module. And this is an analog module. It supports a single receiver transmit site. And there are 12 of them on the right side of the voter. You can stack 3 of these voters to support up to 36 receiver sites. We can go beyond that by doing multiple tier voting. In essence, that site voter module contains a digital signal processor that measures the spectral noise. We have the delay buffers so we can slow the audio down to match the late arriving audio. And we have gain controls such that we can create seamless handoff between the different receiver sites. So this module has been around for quite a while. Its primary backhaul method is analog 4-wire. Lease line, tie lines, voice grade lines, T1 microwave, but not IP links. So some of our engineering development folks have come up with a solution to vote over IP links. And this is the new SVM-3 module. We're currently in alpha and beta testing right now. Hopefully is going to be in production very soon here. And I think Dave mentioned that it is available for sale now. But the SVM-3 module is a purely digital module. It's a 3-site module as opposed to the SVM2 is a single-site analog module. This SVM3 module will support 3 remote receiver sites, and this works in conjunction with another module called a QMT-1 module, stands for Quality Measurement and Transport module. This module resides directly at the receiver site, so this alleviates a lot of things. One of the most important things it alleviates is it measures the spectral noise immediately from the receiver site. We don't have to compress the audio through vocoders, lossy vocoders, deliver it to the vocoder in a degraded fashion and misvote. We're going to measure the spectral noise, 2.2 kilohertz in this case, directly at the receiver site. And we can, again, support 3 separate links. The QMT module contains the digital signal processors as well as the digital filters and the faculties to sense the unsquelched nature of the receiver site and measure the spectral noise. The other thing that the QMT-1 module does, it continuously analyzes the network path length, essentially the virtual latency or the fluctuation of the latency. So the way we do this is through what we call a time sync. And the control processor module, the CPM3, within the analog voter, is essentially the brains of the system. It sets the voting criteria. It controls the rest of the modules. But it also delivers what we call a time sync signature to the parent SVM3 digital module, which then in turn distributes the time sync to its subordinate QMT modules out at the receiver sites. So what this essentially does, it aligns every QMT module clock. We just want to reference to the control processor modules. We have an ability to use a network timing protocol, but really, for all intents and purposes, it's really not necessary because we're trying to reference the receiver sites to the master or the parent voter itself. So we're continuously sending these time syncs at a rate that's variable. We recommend every 60 seconds realign the clocks at the QMT module. When the site fully quiets, a couple processes begin occurring. The first thing we do is we begin the measurement of spectral noise at the QMT module, and then we place that information, the quality information, into the ROIP packet, and we deliver the ROIP data to the parent SVM3 module, which we then hopefully vote and deliver to the voting system. The second thing that occurs is each of the ROIP packets not only contains the spectral noise, the correlated audio, the voice that we're interested in, it also contains the time sync signature. Once delivered to the voter, the control processor module looks at all the time sync information being delivered from the subordinate sites and realigns the receive audio delay in not only the SVM3 module, but the SVM2 modules on a dynamic basis. So the time sync is important because that signature is contained in the ROIP data. We don't really care anymore how long the physical or the virtual length of the network is. Latency can change, but we don't care. And we do this, again, without any timing sources. So again, we measure the spectral noise at the receiver site, and we place the time signature or the time sync signature into those packets, which are used to reference at the voter, and we dynamically adjust the receive audio delays of not only the analog SVM2 modules, but the digital SVM3 modules, preventing misvoting. How do we sell the voter? Fairly simple. One of our largest customer base is public safety, and there are a lot of SNV-12 voters out there. A great asset for public safety. So we got a lot of voters across the nation, even worldwide, that are voting public safety. In terms of the commercial world, we have a lot of voters deployed in a linear fashion along toll roads. In this type of situation, you can use a multicast or a simulcast architecture, since we're transmitting and receiving at each of the satellite receiver sites. Again, a large deployment of linear voting architecture. Same holds true with utilities. Utilities primarily use a multicast type of architecture. Again, multicast requires the subscriber unit to change their channels as they move into different regions. So depending on the architecture, RF isolation between these sites, the system can work sort of in a sloppy cast type of situation, or using multicast. Same with transits. We have several voter systems along railway systems, again linear, and air traffic control. And we do have a lot of voters overseas voting air traffic control. We do deploy voters at a lot of the Air Force bases in the United States for air traffic control locally at the Air Force base. One thing that helped us out quite a bit was really the narrow banding, which occurred a few years back, going down to 12 kilohertz bandwidth. And as you can notice here, this is a typical plot. The green was the coverage area when the agency was transmitting at 25 kilohertz. They went to narrowband, and the red depicts the coverage area, which is significantly reduced, which requires more receiver sites to increase the coverage area, requires analog voting. The SNV-12 analog receiver voter is also useful in security deployments, particularly when the facilities or the utilities are separated by many miles. By using multicast, the dispersed sites can also share audio, regardless of the distance between these sites. Not only is analog receiver voting at home in public safety and fire services, but in the commercial world, utilities, as well as transportation, any analog LMR deployment that suffers from coverage issues, even in the commercial world or utilities, the analog voters can be very important, particularly in environments where radio coverage is an issue. All the public safety and fire services utilize our voters quite extensively. Always think about transportation as well as the commercial world. Analog voters will be important to support those satellite receiver sites. So if somebody wants to replace just a single lease line, or they want to transition one T1 microwave link to a digital microwave link, they can simply install one SVM3 module to support a single digital link. It's not a forklift reconfiguration of the system. Again, they can just piecemeal one link at a time if that's the way they want to go. And I talked to a lot of customers that that's the way they want to go, because it's going to be more economical for them transition from lease lines or analog links to digital links. And so you can go visit our website and then receive more information. And again, we have an alpha system that's been running in Raleigh on a commercial system for many months. We've got a couple beta systems being deployed as we speak on live systems, public safety and fire service systems. So it looks like we're on our way to having a successful production SVM3s and QMT-1s. That is it. Got any comments, Dave or Carol?
One thing,
yeah.
We do have about 40 units that are available for sale, and of course we're having more built, but the first request for those 40, get them first.
Okay, yeah, and if you go ahead and visit our website, give us a call. You know who your representatives are out there, Roman Kaluta, myself. Obviously Carol is available.
So I don't have anything further to say. Carol, do you?
Nor do I. Again, I appreciate everyone attending. If you need any additional information, please feel free to give us a call. Let us know how we can support you in any way, your efforts to sell this product. Thank you very much and have a good day.
Thank you, everybody.